So, we will continue our discussion on Bohr model. So, that was the three postulates. So, electron, so what was the model? So, nucleus, Rutherford model, it will rotate in orbit. Now, first postulates of Bohr, it tells that it can rotate in a definite orbit, this orbit or this orbit or this orbit. The orbit, it is defined by these first postulates. The angular momentum has to be quantized and it will be n h cross. So, it has to be h cross, 2 h cross, 3 h cross, 4 h cross, like this. Okay. So, that way one can find out the orbit, and they are stationary orbit, fixed orbit. Okay. And then second postulate is telling there will not be any radiation, when they are rotating in this stationary orbit. Okay. So, from first postulates we get L equal to n h cross angular momentum. So, that is basically mvr. Okay. If radius is r, its mass of electron is m, and its velocity is v, Okay. So, this mvr equal to n h cross. Okay. So, from first postulates we can get, and then here you see from Rutherford postulates or model. So, electrons are revolving in orbit. So, its charge is E, and this nucleus, the charge is Jd. So, Bohr actually he considered one electron system, basically a hydrogen atom or hydrogen like atom. Okay. So, one electron system, if system is having one electron, then because he was trying to explain this hydrogen spectra. So, hydrogen like atom means one electron, it is like helium. Okay. So, it will be one electron if we take out, so it will be hydrogen like atom. Okay. But its nucleus, so lithium, so it has 3 electrons. So, if you take out 2 electrons, so it will be this nucleus, its charge will be plus 3e. So, in general we have taken Jd, Jd is atomic number. So, they are revolving. So, as we know this Coulomb's force Jd into E. So, Jd square by R square. So, that is the force, attracted force. So, electron will try to come, feel force towards the nucleus, and when it is revolving, so there will be centripetal force, basically centripetal force. Okay. So, centripetal force will be equal to the Coulomb force, Okay. So, centripetal force, what is that? So, that is basically m v square by r. Okay. These are standard, you know. So, this is one equation, and second one is we are getting from here. what we are getting. So, let me write this way, just in opposite way. So, basically mv square by r equal to jd square by r square, and other one is mvr equal to nh cross. Okay. So, from here we can get the expression of radius r and velocity of electron in the orbit. So, just is simple, you can find out. So, mv square here r square. So, by m I will take this, and then this r square if I take this side. Okay. So, r square will not be there. Okay. So, mvr equal to n h cross. So, these are n, this I can write as a this I can write n square h cross square by mr equal to jd square. Okay. So, r equal to n square h cross square by m jd square. So, r equal to n square h cross square by m z square. Okay. So, next if you, so let me go back to the mv square r equal to r square. So, that was our original. So, now if I want to find out mv square by r equal to jd square r square. So, so if I this r, this will go. So, this I will take here. Okay. So, mvr equal to n h cross. So, I can write n h cross into r equal to jd square. Okay. So, r equal to jd square by n h cross. So, sorry, not r, m v r, this is v, it will be v. Okay. So, v equal to, I will get z square by n h cross, right. So, one can find this from these two basic equation. Let us go back. So, mv square by r equal to r square. So, that is the original relation, these two relation. Okay. Now, radiation, what is the energy of the, when it will jump from one level to the another level. So, from third postulates. So, energy E equal to, so say E1 E2 minus E1. Okay. So, this will give us energy difference. So, I can write del nu. So, that will come out as a radiation, and it's h nu, or one can write n h nu. Okay. So, what is the energy expression? E equal to, I can write E equal to kinetic energy plus potential energy of the electron plus potential kinetic energy plus potential energy of electron. What is the potential energy? So, there is the z square r square, this force, right. So, potential energy is defined from infinity to taking at distance r. What is the work to be done? So, z square by r square. Okay. dr. So, if you integrate, you will see that it comes minus z square by r. Okay. So, that will be the potential energy. Okay. So, E equal to, I will write minus potential z square by r. Okay. And then kinetic energy half mv square, kinetic energy is half mv square, kinetic energy half mv square, half mv square. So, from here itself you can see mv square. So, half mv square, half mv square. So, this r, so I have to put 2 here. So, this r will go. So, half mv square equal to z square by 2r. So, this half mv square will be equal to z square by 2r. Okay. So, plus z square by 2r. So, this total energy, kinetic energy plus potential energy, you will get minus z square by 2r. Okay. Z square by 2r. Now, if you put the value of r, so what you will get? Energy expression. So, I will move it. So, I will get energy expression E equal to, so n square and mz square. So, I will get minus m z square e to the power 4 divided by 2 n square a square, right. So, that is the energy of electron in a particular orbit, basically nth orbit. Okay. So, from here you can conclude that this radius, one can conclude that radius of the orbit is proportional to the n square. That means, when you will go this first orbit, whatever the radius, second orbit radius will be 4 times, third it will be 9 times. Okay. So, for first orbit, if it is r0, okay, so second one it will be 4 times of that one, third one it will be 9 times of that one. Okay. So, one can draw the orbit, okay, and one can just speculate this, how the radius of the orbits are varying. Second is velocity. Velocity is basically inversely proportional to orbit number. First orbit whatever the velocity, second orbit velocity will decrease, third orbit velocity will decrease. Okay. So, it is inversely proportional, and energy also, its minus sign is there. Third, energy also is proportional to the 1 by n square. Okay. So, in principle, if you know the radius, velocity, energy of the first orbit, so in terms of that you can express the energy velocity radius of the other orbit. Okay. So now this energy difference when it is going from one orbit to the another orbit. Okay. So, this is the energy. So, if I take write it is E n, okay, energy of the nth orbit. So, from third postulates I can write E n, it is when it goes from n2 to E n 1. Okay. So, this we can get so this n2 n1 n2 is higher than n1. Okay. So, basically when from higher energy level to the lower energy level it jumps, then it's emit, and other it actually absorb. Okay. So, here we are considering the emission of radiation from atom due to jump of electron from one orbit to the another, from higher orbit to the lower orbit, lower energy orbit. Okay. So, this E, for this I can write m z square e to the power 4 by h cross square. Okay. Then since minus sign is there, so you will get 1 by n1 square, 1 by n1 square minus 1 by n2 square. Okay. Where n1 into where n1 into n1 can take 1, 2, 3, 4, etc. N2 can take 2, 3, 4, 5, okay, etc. So this will be so it will this energy difference will give us radiation, and that radiation is energy is h nu, okay, according to third postulate. So this energy is h nu. So from here I can write this nu equal to m z square e to the power 4 divided by now here I am missing 1 2, I have to put 2 basically here, yes, 2 and h square by 4 pi square. So 4 pi square, so 2 basically 2 pi square, so that I can take off. So here I can write 2 pi square m z square e to the power 4. Now h square, h cross, it will be h, that is square, and now the other side h nu, so it's h cube, okay, and then 1 by n1 square minus 1 by n2 square. And generally, as I mentioned that or Bohr empirical formula we have seen, it was written Bohr empirical formula that was written that nu bar equal to r 1 by n1 square minus 1 by n2 square, okay. So, that is the empirical formula. In 1885 it was given to to explain this atomic spectra. So, and from Bohr model, whether we can get this or not. So, that is the first, if we get so, it will be able to explain that one, and we are going to achieve that one. So, nu equal to, it is basically C by lambda. So, this is written 1 by lambda is 1 by lambda is generally is written nu bar, wave number is nu bar. Okay. So, nu bar. So, this we can write C nu bar, C nu bar. So, actually you are getting then nu bar. So, if I write C here, so they can, then I can write nu bar here. Okay. So, nu bar equal to this. So, now to compare with this Balmer empirical formula, that is why we have to, so nu bar equal to here R one by n1 square minus 1 by n2 square. So, when, so this is the exactly, this theory gives exactly this empirical formula, which was able to explain this spectra, okay, hydrogen spectra. So, but unfortunately, so this now R is known, and it is called Rydberg constant. R is Rydberg constant. R is Rydberg constant, and its value from here all are constant. So, if you put the value, and that value is 109,737, 109,737 centimeter inverse. Okay, if you put the value in this. Now, this was slightly different than this value. This value means this constant was taken, chosen in such a way, so that this it fit the experimental data, it explained the experimental data. So, this value was basically taken, that is the experimental value. This value was taken 109,677, 109,677, 109,737. So, it was slightly higher, this value was slightly higher than the experimental value. Okay. Otherwise, everything is fine. So, this value can explain, can get reproduce this wavelength or in terms of wave number. Okay. So, that is why it is we write this R infinity. Why we are writing infinity? So, you know that that again it was started to rethink why this discrepancy, why this difference is coming. Then it is realized that this actually here we have considered the nucleus is of infinite having infinite mass. So, it is at rest, it was considered the nucleus is at rest and only electron is rotating, moving. Okay. So, this is only possible when this nucleus mass will be infinity, but it is not the case, its mass is finite mass, its mass is finite mass m, capital M. Okay. And So, one has to consider that finite mass of the electron, and if it is mass is finite, then it is not only the electron is moving. So, electron and this nucleus both are moving, okay, with respect to the center of mass, So, if we consider the center of mass, so it is electron, it is the nucleus. So, both are rotating with respect to a axis passing through the center of mass. Okay. So, this center of mass, see, this is capital M, this is small m, it is a, this is B, okay. It is rotating with omega, angular velocity omega. So, from here one can find out, so whether I should complete it. So, from center of mass m into AC, that distance, it has to be equal to the m into BC, that distance. Okay. If this distance, between this distance is nucleus and this is R. So, this is R. Okay. So, basically AC I can replace m into R minus BC, equal to m BC. Okay. So, you will get BC equal to we said m plus m, okay, and other side m by m plus m into R. Okay. Similarly, you can find out AC equal to m by m plus R. Okay. Okay. So, total angular momentum will be L, L. So, this angular momentum of this one m omega square R, not R, with respect to this m omega square AC plus m omega square, sorry, small m omega square BC. Okay. BC. So, put value of AC and BC, and you can show that it will come like this, m omega square R. Okay. So, this if you write mu omega square R, okay, mu omega square R, or it is equal to mu omega into R is V basically. So, we can write, okay. So, earlier we took this angular momentum mv square by R, now it is writing mu v square by R, okay, mu v square by R. So, m, if you replace m by mu, then all expressions are valid. So, in that case we are considering considering that the nucleus is not at rest, it is also moving with nucleus as a whole with respect to center of mass. So, this mu is called reduced mass, Why? Because mu is less than m, from here you can show mu is less than m. Okay. So, now this m, just we have to replace is fine, energy, where is energy? So, this m we have to replace by, okay. So, mu is less than m, okay. So, then now if you consider, so this Rydberg constant, so mu is less than m, so it will be reduced, okay, and it will basically reduce and it will give this value. Okay. So, that is the now fact. It's so this Rydberg constant, this value is for when you are considering the nucleus is of infinite mass, it is at rest, but in reality it is not the case, and one has to consider the that both electron and this nucleus both are rotating with respect to the center of mass, and you will get reduced mass, and then it will give you exact that Rydberg constant which is experimentally found. And now this from Bohr theory first time, this spectra, hydrogen spectra was explained. Okay. So, I will stop here and I will continue in next class. Thank you.